Today we're going to cover pH of salts, polyprotic acids, and predicting acid strength. And this will wrap up our notes for chapter 15, which is the first half of this unit on acids and bases. So the first thing we're going to talk about is the acid-base properties of ions and salts. And so as I told you before, you know that the anion that you get after an acid donates its proton is a conjugate base. And so it turns out that any ion can be the conjugate base of an acid. If we just add a proton back, then we get the acid that we would have started with. So for example, F- is an anion, and the acid that would go with it if it was a conjugate base is HF. All right, so depending on the acid that you would get, the strength of that anion is going to vary. So over here I have a chart, and this chart is also in your book. It's on page 725. And you can see that the stronger the acid is, the weaker the conjugate base is, which we also talked about already. So for example, Cl- is the conjugate base for HCl, but HCl is a strong acid, and so Cl- never picks a proton back up because HCl always dissociates completely. So in the case of strong acids, the anions that you get are going to be neutral. So any of those 6 strong acids that I had you learn, any of those, the anion that you get after it donates its proton, those are all neutral in solution. They don't act as a base. But if you go down to weaker acids, the conjugate base that you get, those anions can serve as reasonably strong acids comparatively. So for example, HCN is a weak acid, so Cn-, which is the conjugate base of that, which is also an anion, is going to be a pretty strong base. Okay, so here it asks us to classify each anion as either basic or neutral. All right, so NO3-, that is the anion that you get after nitric acid reacts, and nitric acid is a strong acid, so NO3- is going to be neutral in terms of pH. NO2 is the conjugate acid or conjugate base, that you get when nitrous acid reacts, which is HNO2, and so nitrous acid is not one of the 6 that are on our strong acid list, and so this solution, an NO2- solution, is going to be slightly basic. Okay, and then the third one is C2H3O2-, and this is the conjugate base of acetic acid. Acetic acid also is a weak acid, and so the acetate ion in solution is going to be slightly basic as well. Okay, so the converse of this is that every cation is the conjugate acid of a base. So all we would need to do to get the base back out would be to add an OH- to that cation, or in the case of conjugate acids of weak bases, you would just remove the proton that was just added. So for example, if we had sodium ion, which is just Na+, if we were to want to make that into a base, it would just be NaOH, right? And NaOH is a strong base, so the sodium ion itself would be neutral. It wouldn't act as a very good conjugate acid. But if you had, for example, NH4+, NH4+ is the conjugate acid of NH3, which is a weak base, and so NH4+ is also going to act as a decent acid, so that solution would be acidic. Okay, so now if we want to classify each cation as acidic or pH neutral, the first one we have here, C5H5N+, that one would be a weak base because it's a hydrogen attached to a nitrogen, and so that particular conjugate acid would be a good conjugate acid, and so that solution would be slightly acidic. Ca2+, that would be the conjugate acid of calcium hydroxide. Calcium hydroxide, because it's an alkaline earth metal combining with a hydroxide ion, that's a strong base, and so calcium would be pH neutral. And then chromium 3+ is not an alkali or an alkaline earth metal, and so it's not going to form a strong base. But for these, actually, the rule is a little bit different. So, and I don't know that you need to know this for the AP exam, but we're going to go over it just for the sake of completion. So when you have cations that are small and have large charges, so things like aluminum 3 plus or iron 3 plus or chromium 3 plus, those all form weakly acidic solutions. So if it's not in the alkali earth or alkaline earth column, and it's a cation that has a charge of more than 2 plus, you can probably assume that it's going to be acidic in solution. So now that we've looked at these qualitatively, let's take a look quantitatively as well. So if we have a solution, it's a 0.100 molar NaCHO2, what is the pH of that solution? So you should be able to tell, hopefully at this point, that if it completely dissociates into Na plus and CHO2 minus, the Na plus is going to be neutral because that's the conjugate acid of a strong base. And CHO2 minus, which is the formate ion, is the conjugate the conjugate base for formic acid, which is a weak acid. So this is going to be a slightly basic solution, but we actually have the tools at our disposal now to figure out what the pH of that solution is going to be. Okay, so the trickiest part here, or the only new part really, is finding what Kb is for this conjugate base. Okay, and we can use Kw is equal to Ka times Kb for any particular acid or base. So in this case, the Ka for the formic acid times the Kb for the formate ion is going to be equal to Kw. All right, and as a refresher, Kw is 1 times 10 to the minus 14th. So we have that equals 1.8 times 10 to the minus 4. That's the Ka for formic acid. You can find that on your book. There's some on the table on page 705, and there's also some in the appendix. And it's going to be that times Kb. So if we solve for Kb, we get 5.56 times 10 to the minus 11th. So that's a pretty small number. Okay, and now to figure out what our pH is, we're going to have to set up an ice table. So if we take our conjugate base plus water, we're going to get OH minus plus HCHO2. Okay, so, and the Kb for that reaction, or the equilibrium constant for that reaction, is the Kb we just found. All right, so our initial concentration of formate ion is 0.100 molar, and the other two are going to just be 0. And then our changes are going to be minus x, and plus x. And our equilibrium constant of the formate ion is still going to be 0.100 because our equilibrium constant is so small that it's not going to change enough that we could see a difference. And our concentration of OH minus and formic acid are just both going to be x. All right, so we have Kb is equal to x squared over 0.100, which means that x is equal to 2.36 times 10 to the minus 6th, right? And that's our OH concentration. So if you remember, Kw is also equal to the concentration of OH minus times the concentration of H3O plus. So we can find the concentration of H3O plus by plugging in our 2.36 times 10 to the minus 6th in for the OH minus concentration. All right, so if we divide that on both sides, we get H3O plus is equal to 4.24 times 10 to the minus 9th molar. All right, now to find the pH, we need to do pH is equal to the negative log of 4.24 times 10 to the minus 9th, and that is equal to 8.372 as our pH. All right, now that we've gone over whether a solution is acidic, basic, or neutral with one particular ion, we would need to figure out how to determine if it's going to be acidic, basic, or neutral if you have a salt, because there's usually a cation and an anion present. So there are 4 different situations that you could encounter. The first is that the salt is composed of a cation and an anion that neither one acts as an acid or a base. So an example of this would be sodium chloride. And since sodium is the conjugate acid for a strong base, chloride is the conjugate base for a strong acid, they would both be pH neutral. And so salts in which neither the cation nor the anion acts as an acid or a base form, sorry, there's a typo there, pH neutral solutions. Okay, so the second case would be salts in which the cation does not act as an acid and the anion acts as a base. So an example of this would be, again, the cation could be sodium because that's the conjugate acid for a strong base, so that doesn't form any acidic solution. And then the anion would be something that does act as a base. So, for example, F-, which is the conjugate base for a weak acid, those would form basic solutions. Okay, if you have a salt in which the cation acts as an acid, but the anion does not act as a base, then you would get an acidic solution. And so an example of this would be something like an ammonium ion as a cation, and chloride ion is your anion. So the chloride ion doesn't contribute to the pH, but the cation does contribute, and so overall you would end up with an acidic solution. Okay, and then the final one, which is the most complicated of the four, is salts in which the cation acts as an acid and the anion acts as a base. And so that sort of solution is going to depend on the pH of the relative strength of the acid and the base. So in that case, we want to compare the Ka of the acid to the Kb of the base, and whichever of those is bigger will dominate, and so therefore a bigger Ka would mean an acidic solution, and a bigger Kb would mean a basic solution. All right, so let's do a couple of examples here. Determine if the solution formed by each salt is acidic, basic, or neutral. So for number one, we have SrCl2. The Sr2 plus ion is the counter ion of a strong base, so that would be pH neutral, and the Cl minus is a counter ion for a strong acid. So that solution would be pH neutral. AlBr3, which is number two. Al3 plus is one of those ones that's going to be weakly acidic in solution, but Br minus is the conjugate base of a strong acid, so that one's not going to be a factor, so this solution would be slightly acidic. Okay. Number three, we have NaCHO2, and so Na, again, was the counter ion for a strong base, whereas CHO2 minus is the anion, which is a conjugate base for a weak acid, and so this is going to be a slightly basic solution. And then for the fourth one, we have NH4 plus, which is an ion that's the conjugate acid for the weak base ammonium, and we have F minus, which is the conjugate base for a weak acid, HF. So I'll go to the next slide so we can figure out how we would make a comparison of the Ka and the Kb in this case. All right, so let's start with the NH4 plus. So the Ka for NH4 plus, we're going to have to find using Kw. So Kw is 1.0 times 10 to the minus 14th, and we know that the Kb for NH3 is 1.76 times 10 to the minus 5th. So we'll get Ka is equal to 1.0 times 10 to the minus 14th divided by 1.76 times 10 to the minus 5th, and that equals 5.68 times 10 to the minus 10th. All right, so for the Kb for F minus, we'll have to do the same process but go in the other way. So Kb is going to equal Kw over Ka for HF, and so that's equal to 1 times 10 to the minus 14th divided by 3.5 times 10 to the minus 4th. And you can look that Kas and Kbs up in your book, and you will not be expected to know them. They would be provided to you. All right, and so then Kb is equal to 2.9 times 10 to the minus 11th. Okay, so since Ka is bigger than Kb, because negative 10 is a larger exponent than negative 11, then that tells us that this will be an acidic solution. Okay, now we're going to switch gears just a little bit and talk about polyprotic acids. So a polyprotic acid is an acid that ionizes in successive steps, each with its own Ka. One example here is phosphoric acid, which is H3PO4. And so there are three potential protons that can be lost in this acid. So if we just lose one, we get H2PO4 minus. If we lose a second one, then we get HPO4 minus 2. And if we lose the third one, we just end up with the phosphate ion, PO4 3 minus. Okay? And so if you look at the Kas for each of these steps, Ka1 is 7.2 times 10 to the minus 3, which is a pretty big Ka compared to many of the ones we've looked at. Ka2 is 6.3 times 10 to the minus 8, so that's a little bit smaller. And then Ka3, 4.6 times 10 to the minus 13th, that's the smallest of all of them. And so you can see they get progressively smaller as we continue to pull off protons, and this makes sense because the phosphate ion has a -3 charge to hold on to those protons with, so it's going to be able to hold on to 1 much more tightly than it's going to hold on to 3, for example. So each one that you pull off takes just a little bit more, or is a little less likely to come off, I guess is the best way to put it. So in your book, they go over how to calculate the pH of a polyprotic acid system. We are not going to do that in this class. It's outside the scope of the AP curriculum, but it's there if you want to take a look at it. What I expect you to do is know that each successive proton comes off a little bit less, so the Ka gets smaller and smaller for each ionization, and then you should also be able to write these stepwise ionization reactions. So as an example, let's do the one for sulfuric acid, which is H2SO4. Okay, and then the first ionization of sulfuric acid is actually strong. So H2SO4 dissociates, and you get HSO4 minus, which is aqueous, plus the H3O plus. And then for the second ionization, you have HSO4 minus plus water, which goes to H3O plus SO4 2 minus, okay? And so the first one of these is strong, but the second one is not, and that's because the Ka gets smaller with each successive ionization. So let's switch gears one more time, and this is the last thing I'm going to talk about today. I've had you learn that there are 6 acids that are strong, and then you can just assume that the rest of them are weak. But there is some trend that happens with the strength, and you can make predictions about relative strength of acids based on their structures. And so there are 2 different kinds of acids we're going to talk about. The first is binary acids. So binary acids, you just have a hydrogen that is bonded to one other atom. So HFCl, HCl, HI, HBr, those are all examples of binary acids. Okay, so there are 2 things that factor into the acid strength. The first is the bond polarity. So the more polar a bond is, the more acidic it's going to be. Okay, so you'll notice that in the table I've shown here, if you look at column 6A versus 7A, the acids that you get if you have an element from column 6A, which is oxygen, sulfur, etc., those acids are not very strong. And if you go to over one more column where the electronegativity is a little bit higher, those are stronger acids. So as the element that is bonding with the hydrogen is farther to the right in the periodic table, or the electronegativity goes up, the acid strength goes up. Okay, the other factor that influences that is the bond strength. And so you might say, well, if polarity is such a factor, then why isn't HF a really strong acid? Because F is the most electronegative atom. And that's because the bond strength is also a factor. So the HF bond is the strongest of the halogens with hydrogen, and then it goes down from there. So you can see in this figure I've put on here that as you go down the periodic table, the bond strength decreases. And so that results in HF not being a strong acid because those 2 things together cause it to, the increased bond strength causes it to not dissociate completely. Okay, so maybe that will help you remember which of the binary acids are strong and which ones are weak, maybe. Okay, and then the second thing we're going to talk about are oxy acids. So oxy acids are acids where you have a hydrogen that's bonded to an oxygen atom, as it sounds, and the oxygen atom is also bonded to another atom. And in this case, we're calling that other atom Y. And what Y looks like has a big impact on how easily that hydrogen is donated and how strong that acid is. So as the electronegativity of Y increases, it weakens the OH bond, and the acid becomes more acidic. So as Y is pulling electrons toward it, it is pulling them away from the O, and that O is left is allowed to be donated more easily. So as the electronegativity of Y increases, the acidity of the oxy acid also increases. Okay, and then the other thing that's a factor is the number of oxygens that are bonded to Y. So as we add oxygens to that Y atom, those oxygens are very electronegative, and so they'll continue to pull electrons away from Y, which again decreases the strength of that OH bond and lets the O go more easily. So as the number of oxygens that's bonded to Y increases, the strength of the acid also increases. Okay, and there's a table in your book that compares some of those. But this is the reason why, for example, sulfuric acid, which is HSO4, is strong, but HSO3 is not strong. It's why nitric acid, which is HNO3, is strong, but HNO2, which is nitrous acid, is not strong. So hopefully these trends will help you remember the 6 strong acids, but it also will help you make predictions about the relative strength of acids without the Ka values.